All right, good morning, everybody. So today we'll continue our discussion about testing whether a given series is convergent. But let's do a quick recap of what we did last time. I guess last time we defined convergence in layman's term or informally as the existence of a finite value for the infinite series. So if you will be able to get the finite sum out of a series, then it is convergent, and otherwise it's divergent. So it's actually kind of an intuitive way to see if it's an easier way, at least intuitively, to see if it is divergent. Because if you cannot imagine, or if you think you cannot get a finite sum, then automatically it is divergent. All right. Now, saying that it is convergent is, I think, is tougher than saying it is divergent. But anyway, so for that, we define convergence to be the existence of a limit of the sequence of partial sums. And usually that's hard to do. But thankfully, there are some basic series that we can take advantage of later when using other tests, because this basic series already has established criteria for being divergent or not. So for instance, we look at geometric series, which you said are series of this form. We have a scalar multiplier A times a ratio R, which is raised to the indexing variable. Now we say it is convergent if the magnitude of R is less than 1. So we will get a finite sum, it turns out, if the absolute value of R is less than 1. And more than that, we have the formula for that finite sum. It's going to be A over 1 minus R. Okay. Then we also look at P-series. Well, what are P-series? The P-series are series of the form 1 over the index variable raised to a constant P. And the convergence of this P-series will rely on the value of P. If P is greater than 1, it's convergent. Otherwise, it is divergent. Okay? So that's how we know that the summation of 1 over n squared is convergent. Why the summation of 1 over n to the 3 halves is also convergent, right? They are basic examples of P-series. A special P-series is what we call the harmonic series. If P is equal to 1, you'll have the harmonic series, which is divergent. No questions asked. All right. And then we also, I think last time, look at one example of a telescoping series. And the strategy to determine if it's convergent or not is to look at the sequence of partial sums. And I'll illustrate this again as a review later with the question sent by Brian. Okay. And then we also had our first test, or our first true test for convergence or divergence is the basic divergence test, which tells us all we need to do is to look at the limit of an, take the limit of whatever is inside the summation as the index variable go to positive infinity. If the limit is not equal to 0, then the series diverges. And I hope you can visualize why that is the case. Because, well, if the limit of an is not equal to 0, so if you expand this to a1 plus a2 plus a3 plus ... until an plus 1 and so on, these terms in the last few terms will never go to 0. That means you will have infinitely many addends that are not equal to 0 in the tail end of your summation. So if this guys will not be equal to 0, you'll end up adding to the large sum. So there's no way that you'll get a finite answer. That's why the series diverges. Okay. So if the limit of the nth term is not equal to 0, then the series is divergent. All right. Now, be careful. That's the only thing that the test for divergence can do. It can only conclude the divergence of a series. Because if the limit of an is equal to 0, no conclusions can be made. We need to try another test. So we'll illustrate that later, but let's review how to deal with telescoping series first. And I'll do so by illustrating Brian's example here. Though we did problem 40 last time, which is very similar. So, but just to recap, let's do this. I'll just label it with a bullet. I don't know what number it is now, but okay, let's try this. K from 2 to positive infinity of 1 over k squared plus 2k. Now, if you have a complicated fraction inside a summation, oh, by the way, I mentioned try basic divergence test first. So look at the n term or the k term, 1 over k squared plus k. What will happen when k approaches infinity? When k approaches infinity, this will go to 1 over infinity, right? Which is equal to 0. So the test for divergence is inconclusive. So we need to try another test. Now, if you see a complicated denominator, there's a big chance that this is a telescoping series. If you're suspecting that you have a telescoping series, do a partial fraction decomposition. So here we try to decompose 1 over k squared plus 2k in terms of partial fractions. And this is the same strategy we did for chapter 8. So we need to factor the denominator. Okay, and then we'll have two partial fractions because the denominators are both linear, non-repeated terms or non-repeated factors. So the first partial fraction will have k. The second partial fraction will have denominator k plus 2, and their numerators are unknown constants a and b. Okay, so this implies, again, strategy we did in chapter 8, that 1 is equal to a times k plus 2 plus b times k for any k, right? So let's take advantage of that fact. So I can give killer values for k. I can choose k to be equal to -2. So that means 1 is equal to -2b, implying that b is -1/2, right? And then if k is equal to, what's the other killer value? 0. If k is 0, we'll get 1 equals 2a, meaning a is equal to 1/2. So what we get here is that the given summation as k goes from 2 to positive infinity can be rewritten in terms of the partial fraction decomposition. We have a over k, so that's going to be 1/2 over k plus -1/2 all over. Okay. Now I'll simplify this a bit. I will factor out the -1, the 1/2s, all the way out of the summation. So I'll have a 1/2 here, summation from 2 to infinity of 1 over k minus 1 over k plus 2. That's how the series looks like. And if you have something minus another term that depends on k, it is a telescoping series. Because we'll see when we expand the partial fractions, we'll see that the middle terms will cancel each other out, or most of them will cancel each other out. So again, telescoping series, we look at the sequence of partial sums. So let's start at S2. S2 is the sum from the start of the summation until the second term, or the term when k equals 2. So this would be 1/2. And then I'll plug in k equals 2 to this guys. So what we'll get is 1/2 minus 1/4. That's the first partial sum. The second partial sum is when k is equal to 3. So this would be 1/2 times, you plug in starting from 2 until 3. So we start with k equals 2. Oh, that will just be the exact thing I got earlier. Okay, plus, what do I get when k is equal to 3? When k is 3, you plug in 3 here, we'll get 1/3 minus 1/5. That's the second partial sum. I don't think we can do anything about this so far. No patterns are discernible yet. So I'll go to S4. For S4, it's going to be the sum of 3 terms, the first 3 terms in the sum. So we already knew that this will comprise the first two terms. All right. Plus the third term would be the case when k is equal to 4. Plug in k equals 4 there. So we get 1/4 minus 1/6. And I guess here we can do something because, oops, I have a 1/4 here and I had a minus 1/4 there. So it looks like there would be how many? 4 terms left. Okay. Now, if the pattern is not yet clear, go ahead, go at S5. So S5 would be the sum until k equals 5. So I already know that I'll have this. Okay. Oops. Plus, what do I get when k is equal to 5? When k is 5, I'll have 1/5 minus 1/7. So I'll have 1/5 minus 1/7. Okay. Now, can we cancel some things? Yes, I have a minus 1/5 here, and I have a positive 1/5 there. It turns out, oh, I still have how many terms? I'll have still 4 terms left, right? And then if you look at the pattern, it seems that 1/2 will It seems that 1/2 can never be canceled, right? Because if you can look at the pattern, if you go on here, you will have what? I guess we'll have 1/7. Oh, sorry, we'll have 1/6 minus 1/8, right? So there's no way we can get a 1/2 in the tail end of the summation because the denominators will just keep on increasing. The same as 1/3. 1/3 will not be canceled because 1/3 will not appear anymore here in the tail end, right? But okay, so it seems that they will be the mainstays. So if you continue the pattern, let's try to devise what happens to SK. So I'll have a 1/2 scalar outside. Then again, 1/2 seems to be to remain. 1/3 will also appear to remain. Okay, but what would be the last 2 terms? At least looking at the pattern, 2 terms will turn out to be negative fractions. So I'll have a negative here and a negative fraction. But how will those fractions look like? Well, if you look at the pattern, for S4, we got the 1/2, we got the 1/3, but what would be the 2 negative trailing fractions? We have minus 1/5 and minus 1/6. So when k is 4, we'll have minus 1/5 and minus 1/6. If k is 5, we got minus 1/6 and minus 1/7. So it seems that here I'll have what? 1 over k plus 1. Because again, when k is 4, I'll have a minus 1/5. When k is 5, I'll have a minus 1/6. So it seems that it's 1 larger than the subscript, right? So what do you think will happen to the last? Oh, what should be the last term? So I hope you're getting the pattern. What will be the last term? Anybody? So you look at k equals 4, we get a 6. When k is 5, we get a 7. Yeah, Kevin, you're correct. It's going to be k plus 2. Okay, so this is the k partial sum. And remember, the limit of the partial sum is also the limit of the series. So we'll take the limit of sk as k goes to infinity. Basically, we're computing the limit of this guy as k approaches infinity. Okay. Now what happens when k becomes large? 1 over k plus 1 will go to 0. 1 over k plus 2 will go to 0. So eventually this is just 1/2 times 1/2 plus 1/3, which is basically 1/2 times what? 5/6. So that's going to be 5/12. So that's the limit of the partial sums. So therefore, the series is convergent, or you can also say it converges to 5/12. Or in other words, the sum is equal to 5/12. Okay? Does that make sense? All right, you're welcome, Brian. How about the others? Is that okay? Okay, I hope it is. Okay, any questions about this? Or can we go to the next worksheet, which is about the integral test and comparison tests? Okay, great. So let's try the next worksheet. I already uploaded a blank version of it in my website, so you can check it out there. Okay, so this is about the integral and comparison tests for infinite series. Now let's outline what are the steps in applying these two tests. Actually, for the integral test, okay, for the integral test, what we do is this. You will be given a series, okay? Say starting from, you can start at any constant that you like. Say it's a constant 1 to positive infinity. You can start at 2, 3, or 0, or whatever. As long as you start at something constant to positive infinity, first thing to do is to define, we need to define f, the real valued counterpart of an, so that an is equal to fn. So basically, we'll just extend the sequence an, or the n term an, to its counterpart, real valued counterpart f. Then check if f is positive and decreasing. So that's a requirement. You can only use the integral test if the function is increasing. If the function is positive and is decreasing. Okay. Then if the improper integral from 1 to positive infinity of f of x dx converges, so does the series. Otherwise, the series diverges. So this tells us that if you can transform, or if you can, if you look at the real valued counterpart of the nth term in the series, say the function f, if f turns out to be positive and decreasing, then the convergence of the series depends on the convergence of the improper integral. So compute the improper integral. If it is convergent, then so will your series. If the improper integral diverges, then it is, or the series is also divergent, right? Though I think you will realize that it's a bit difficult because you need to compute the improper integrals. So usually the integral test is my last resort because I don't like evaluating improper integrals. But if you are left with no other choice, then evaluate the integral and then see if it converges or diverges. And then in either case, you can make a conclusion about your series. Okay. So that's the integral test. The other test in this section would be the comparison test. So there are two versions at least of the comparison test that I guess was given in the lecture. Okay. Now first you can do direct comparison. I usually abbreviate this as DCT, the direct comparison test. And what you do actually here in both versions of the comparison test, you need a testing series. So you need a testing series. Let's call the testing series BN, which you know to be convergent or divergent, right? So the thing here is you need to think of a testing series, say BN, but make sure that you know whether that converges or diverges. And then we will compare the given series with the testing series. So for the direct comparison test, if the given series is less than the testing series, and the testing series is convergent. So the idea here is you have a testing series that you know to be convergent. And again, the layman's interpretation of being convergent is that you get a finite sum, right? So this gets a finite sum. And if you will be able to show that the given series is smaller than the testing series, you're saying that the given series is less than a finite value, thus making this finite as well, right? So if you have a hunch that your series is convergent, then all you need to show is that there exists a larger convergent series. So here your conclusion, then the sum of AN converges. Okay. On the other hand, if your given series happens to be larger than your testing series, and the testing series is divergent, okay? Again, what's the layman's interpretation for divergence? That means Bn is infinite, right? If it's infinite, so this is infinite, and your given series is larger than that, so that means this must also be infinite. And so we can conclude that the given series diverges. All right. But unfortunately, this is the farthest that we can go. For the other cases, we don't have any conclusion, right? So you can only conclude that your given series is convergent if it is smaller than a convergent series. If your testing series is divergent, then all we know is that this would be smaller than a divergent series, then there's no conclusions to be made. You need to try another test. In the same manner, if your given series is larger than a divergent series, for sure, this will diverge. But if this is larger than a series which is convergent, right? No conclusions can be made because this could still be convergent, just having a larger sum than the sum of BNs, or this could be infinite, and an infinite value is always larger than a finite number. So there are still two possibilities here. So in that sense, the direct comparison test is a little bit limited in scope because these are the only two cases where we can draw conclusions. Otherwise, you need to try some other tests. Now, there's another version of the comparison test, which is the limit comparison test. Which tells us, okay, you can take the limit of AN over BN as n approaches infinity. And if this turns out to be a finite number, okay, then how do I write it? then the two series either both converge or both diverge. Okay, what's the reasoning behind that? Well, this statement, getting a finite limit for the ratio, that means that the terms in AN and in BN grow proportionally. So if they grow with the same rate or with a proportional rate, that means wherever AN goes, BN will also go, right? So if they will share the same convergence or divergence, that's why for the limit comparison test, we usually choose BN to be something that grows in the same rate as AN, so that you get the finite limit and you can conclude whether they are both convergent or not. Okay. So I hope that gives you an intuitive sense about these tests. Okay. Probably it's much easier to look at a couple of examples to see these tests in action. So let's do that. So I have here the exercises from the textbook. You can try them. But I'll start with some ad hoc examples before we look at those things in the worksheet. So let's try, say, number 1. Check whether the integral of n e to the minus n squared and going let's start let's start from, say, 0 to positive infinity. Okay, and check whether this is convergent or not. Okay, now as I mentioned, you can always start by trying to use the basic test for divergence. But if you do that, you can rewrite it as n over e to the n squared. And you see that the denominator grows a lot faster than the numerator because it's exponential. The numerator is just linear. So this will go to 0. So the basic test for divergence won't apply because the limit of an is equal to 0. So we need to try another test. Well, here I'll do the integral test, but I need to make sure that the integral tests apply. So first note that f of x, the real valued counterpart of an, is x e to the minus x squared, which is always positive or equal to 0. So it's non-negative for all x greater than or equal to 0, right? This guy is always non-negative times another non-negative number whenever x is greater than 0, then this is true, right? Maybe I should amend my integral test here. Actually, you can say that it could be there. Could be greater than or equal to 0. All right. And then is it decreasing? Is it obvious that this would be decreasing? Well, one way to check if it's decreasing or not is to look at the derivative. So if you look at f prime of x, this would be what? This would be 1. Sorry, I need to apply the product rule. So this would be x times the derivative of the second factor. It's e to the minus x squared times negative 2x plus copy the second derivative of the first, right? So if you simplify, this is minus 2x squared e to the minus x squared plus e to the minus x squared. And this is what? This is 1 minus 2x squared e to the minus x squared. And what can we say about this guy? Well, when x is greater than or equal to 0, I'm thinking, okay, when x is 0, I know this is always positive, but will this always be negative? 0. When x is 0, this would be 1, so it's not negative. So hold on. I need to change the starting index. Say start at 1. Start at 1. Okay. Just to make sure that it is decreasing everywhere. Okay. Now, since x starts at 1, when x is 1, this would be 0. But no, actually, it's not 0. It's going to be a negative value. So this is always less than 0. Right? Okay. So this is always equal to 0. So the derivative is always less than 0. And remember, when the derivative is always less than 0, then it is decreasing, right? So f is decreasing. And you can see now why I hate the integral test. Because before I can get to the actual test, which is hard on itself, I need to take care of these two preliminaries. Okay. Oh, Fatuma, do you have a question?
I was trying to type the -1, like the answer for when you plug in 1, but the thing was just, I couldn't.
Okay, that's fine. Yeah. So, but I hope you see the point, right? So the derivative is always less than 0, at least when x is greater than or equal to 1. That's why I need to change it a bit to take care of those technical details. But I hope you are now convinced that f is decreasing. It's always positive. So I can apply the integral test. So for the integral test, we'll look at the integral of f of x dx from 1 to positive infinity. You always start at the starting index. So the starting index here is 1. So we start the summation at 1. Okay, so we start the integral at 1. But this is an improper integral. Remember, we evaluate it by turning it to a limit problem. And take the limit as b approaches infinity. All right? So this is our goal. If we get a finite value out of it, then the improper integral converges, and so does the series. If we get an infinite limit here, so the improper integral will diverge, and so will the even series. Okay. So let's do that. Let's evaluate this guy. Though I don't want to track the changes in the bounds, so I'll compute the indefinite integral first. So x e to the minus x squared dx. I will let u to be equal to minus x squared. Du will be negative 2x dx, or that means du over negative 2 is equal to x dx. So that means this integral would be e to the u times du over negative 2, or that's negative 1/2 e to the u plus c. Let's go back to the original variable. It's minus 1/2 e to the minus x squared plus c. So that's the indefinite integral. So if we go back to our problem, okay, we now know how what's the antiderivative of x e to the minus x squared. It's just negative 1/2 e to the minus x squared. So we need to evaluate it from 1 to b, then take the limit as b approaches positive infinity. Now, if we do so, we'll have limit of negative 1/2 e to the minus b squared minus negative 1/2, so it's going to be plus 1/2 e to the minus 1 as b approaches infinity. Okay, good so far? Right? What happens when b becomes very, very large? Well, if b becomes very large, so that means b squared will be very, very large. So this guy will go to e to the minus infinity. but e to the minus infinity is 1 over e to the infinity. E to the infinity is also a very large number, so it's going to be 1 over a large number. So that means the entire first term will go to 0. So that means this will be 0 plus 1/2 e to the minus 1, which is 1 over 2e, which is finite. Right? So therefore, the given series converges by the integral test, right? Because here we saw that the improper integral converges, and so will the given series. That's a lot of work. Any questions? Does the process make sense? Come on, guys, let me know. Perhaps let's do another example. Yeah, just to get used to it. And until now, the integral test is my last resort. I don't want to do the integral test. So I try other tests first before going to the integral test. So yeah, let's call it example 2. Let's do the summation of 1 over n ln n. N goes from 3 to positive infinity. All right. Now try the BDT first, because that might work, but I guess it won't. Because here, if you take the limit of this guy, this will go to 1 over infinity, which is 0. BDT fails, so we need to look for another test. So here we can define the function f to be 1 over x ln x, which is always positive for all x greater than or equal to 3. I'm only concerned about x's greater than or equal to 3 because the summation starts at n equals 3. I don't care what happens before 3. All right. So here I know it's positive whenever x is greater than or equal to 3. And what else? Well, I guess it's obvious that increasing even without doing the derivative test, because you know when x becomes larger, the denominator becomes larger. 1 divided by a larger denominator becomes a smaller fraction. So the bigger x becomes, the smaller the fraction f of x becomes. So that means obviously this is decreasing without doing the derivative test. All right, so we know for certain that this will decrease. So the integral test holds, so we can integrate from 3 to positive infinity 1 over x ln x dx. Again, this is an improper integral, so we can write it as the integral from 3 to b of 1 over x ln x dx as b goes to infinity, right? So again, I'll compute the improper integral first, or sorry, the indefinite integral first, because I don't want to keep track of the changes in the bounds of integration. So for this case, I'll let u to be equal to ln x. Du would be 1 over x dx, which we have here. X will be replaced by du, and then ln x will just be u. Integral of du over u is just ln of the absolute value of u. Reverting to x, will have ln of the absolute value of ln x plus c, right? So going back to our improper integral, this is equal to the limit of, we know now the antiderivative, it's ln of the absolute value of ln x. but we need to evaluate this from 3 to b as b approaches positive infinity, right? And then let's apply the fundamental theorem of calculus. This would be ln of the absolute value of ln b minus ln of the absolute value of ln 3 as b approaches positive infinity. No problems with this because it's a constant, but when b becomes large, ln b becomes large. So we'll have ln of a large number. Ln of a large number is also a large number. So we'll have a large number minus a constant. So this would be a large number. So that means the improper integral diverges because you get an infinite value, right? So therefore, the given series that's 3, oops, diverges. Okay, it's not that hard as well, it's still hard. So you need to be careful and do the steps carefully. Okay. All right, so try to practice with some of the problems in this worksheet for the integral test. So make sure before applying the integral test, you check if the function is positive and decreasing. Otherwise, we don't have any conclusion, at least for the version that is presented in class, okay? So let me know on Friday if you still had some difficulties with the comparison test, with the integral test, so we can do a couple more examples. But let me introduce for the next 8 or so minutes the direct comparison and the limit comparison tests. So let's see. Okay. Let's try this. Summation of n over n squared minus cosine squared n, and going from 1 to infinity, right? Okay, so I'll try the direct comparison test here. So I'm trying to see what will happen to this sequence, to this series. But I should have an idea of where to compare it to, because remember the direct comparison test is kind of limited in scope, because the only conclusions we can make is that if our series is smaller than a convergent series, or if this series is larger than a divergent series. Now, what do we think will happen here? Well, what can we say about cosine squared n? Remember, cosine is just a number between -1 and 1. So that means cosine squared, whatever the value of n is, will just always be between 0 and 1. So this is between 0 and 1. Okay, so that means in the long run, when n is very, very large, the cosine squared n will have no effect, or will have a negligible effect to n squared, right? So essentially, it looks like that our series behaves like what? It looks like it behaves like n over n squared, right? But what is this? This is the summation of 1 over n, which is what? Is it convergent or divergent? Because remember, you need to know whether the testing series converge or not. So is 1 over n convergent or divergent? Unfortunately, no, Fatuma. Nice guess though. It is divergent because it's a harmonic series, right? Or it's a p series with p equals 1. So this is divergent. So my guess is that this will also diverge because they kind of behave in almost the same way, except for the cosine squared end here. Okay. So my goal now is to compare this with a divergent sequence, with a divergent series. Okay. Now, would you agree that this is larger than the summation of n over n squared? Okay, I hope you do because cosine squared is positive, right? So meaning here we have n squared minus a positive number. So that means this denominator is smaller than this denominator. And the smaller the denominator is, the larger the fraction becomes. So here we decreased, what? So here we increase the denominator from n squared minus cosine squared. We make it bigger by making the denominator just n squared. So the denominator in here is larger. So that means this fraction is smaller, right? And hence I have this inequality. But as we have mentioned earlier, this just reduces to 1 over n, which is divergent because it is a harmonic series. Okay. And what we have here, the given series is larger than a divergent series. And so by DCT, the given series also diverges. Okay. Now, if your testing series turns out to be convergent, your series is larger than a convergent series, for instance, no conclusions can be made. It's just that I was lucky that the testing series I used is divergent, and this is smaller than the given series. I like direct comparison test because it's kind of intuitive, but thinking of the comparing series sometimes is hard, or the test turns out to be inconclusive. Okay, let's try another one just to get for you to get familiar with the direct comparison test. Okay, so for this problem, I'll compare it with what? Maybe I can compare it with, it looks like in the long run, the series will behave like n squared over n to the fourth. Because in the long run, when n becomes large, the plus 2 on top and the plus 5 at the bottom will not contribute much to their respective addends, right? So the top behaves like n squared, the bottom behaves like n to the fourth. So that means this guy behaves like 1 over n squared, which is what? A convergent P series. So that's my guess. This would be convergent. And let's see, why will it converge? Well, if I'll use direct comparison test, I'll compare it with this series. Usually it's easier if we just omit something from the denominator. So if I drop the plus 5, that means the fraction we have here is what? The fraction we have here has a smaller denominator, right? It's smaller than the denominator, making the entire fraction larger. Because it has a smaller denominator, the fraction will be larger. So we got this inequality, right? Now, the problem here is I cannot get rid of the plus 2, because if I get rid of the plus 2, I will be decreasing the numerator, and the decrease in the numerator will entail a decrease in the entire fraction. So my next line would have been like this. And I'm messing up with the setup I'm using. So I'll keep on using the single inequality here. But one trick you can use is this. We can write it as sum from n from 1 to infinity of n squared over n to the fourth plus 2 over n to the fourth. Right? I split this up into these two fractions, and then I'll simplify, or I'll split them up. This guy simplifies to 1 over n squared. The second fraction, or the second fraction is 2 over n to the fourth, right? And you see that both are p series with p equals 2 and p equals 4 that are both greater than 1. And remember, if your p series has p greater than 1, then they are convergent. So both series are convergent. Okay. Yes, Bao, I'm trying to make the left fraction smaller. So here, the way I can make this fraction smaller is I'm trying to make the left fraction smaller. So in order to do that, I can decrease the denominator. So there was a decrease in the denominator, making the right fraction larger. Because I have a hunch that this is convergent. And for the DCT to have a conclusion, I need to find a larger convergent series. And I guess that's what we have established here. Upon simplification, the given series turns out to be smaller than the sum of two p series. The first p series has p equals 2. The second p series has p equals 4. Both p's are greater than 1. And so this is convergent. This is convergent. And the sum of two convergent series is convergent, right? So by DCT, this series being smaller than a convergent series is also convergent. Oops. Okay. I love DCT because it's like a puzzle, but sometimes it's hard to do DCT. Actually, the limit comparison test, which we'll illustrate at the start of our meeting on Friday, is equivalent to the DCT, but it is much simpler. Because you don't need to worry about which is larger, which is smaller. All you need to do is to take the limit. And we'll do that on Friday, all right? Now, before we leave, any quick question or clarification? So I suggest you start trying exercises from worksheet 16, and then let me know on Friday if you encountered some difficulties. All right. Okay, great, guys. So thank you for coming today. Enjoy the rest of the day, and see you Friday. Bye.